want to look at the use of the sine cosine tangent ratios, which should be just basic revision for you, GCSE maths. Okay, used with right angle triangles. So if we've got a situation where we've got a triangle with a right angle in it, then if that's the angle theta, and this side is the opposite, the O in SOHCAHTOA, this side is the adjacent, the A in SOHCAHTOA, and this side is the hypotenuse. Okay, and we use that in conjunction with Pythagoras. Whoops. Pythagoras. So I'll give you a chance to revise that, review it, and I'll point you at the right exercises in the textbook. I then want to look at resolving forces into its vertical and horizontal components, and also finding the resultant. So if I have a force here, then I can resolve that into its vertical and horizontal components using this idea of right angle triangle to find those sides, okay, which hopefully is something that you'll be familiar with. So I'm going to give you a chance to review that if you feel you need to. Also, the idea that if I've got a vertical component and a horizontal, or a vertical and a horizontal force, then what is the resultant? And what is the angle theta? And what's the size of the resultant? What angle is that? So going either way, you've either got two forces acting at right angles, what's the resultant? Or you've got a force, what are the vertical and horizontal components? And then the last one I want to give you a chance to look at is it's the sine rule and the cosine rule. The sine rule, A over sine A equals B over sine B equals C over sine C. Ring any bells? And the cosine rule, A squared equals B squared plus C squared minus 2BC. And I want to give you a chance to have a look at those. So the idea is that we're going to look at an example of each, and then I'm going to give the rest of the session over to you, just having a play with some of them, okay? And I'll give you some exercise to look at in the textbook. So exercises are here. I'll come back to that page in a second so you can write them down. Well, no, let's do it now because I'll only forget. So just make a note of those page numbers and those exercises. That's what I want to have a look at. So the first example I want to look at is on page 201. It's work problem number 26. This is worked out in the textbook, so you don't need to write down everything I'm going to do here unless you really want to. You can always print it out afterwards. So let's have a look at it and think about how we might do this problem, trying to ignore what's in the textbook already, because they do it. They might do it a slightly different way. I don't know. We'll see. So a surveyor measures the angle of elevation of the top of a perpendicular building as 19 degrees. He moves 120 meters nearer the building and finds the angle of elevation is now 47. Determine the height of the building. A common technique for a surveyor to use, actually. So let's draw it as they've done in the textbook. So here is our building. So it's perpendicular. That means it's at right angles to the ground. So we've got a right angle triangle. Thank goodness for that. Okay, that makes life a lot easier. A surveyor measures the angle of elevation of the top of the perpendicular building as 19 degrees. So this angle is 19 degrees. He then moves 120 meters nearer the building and finds the angle of elevation is now 47. And he's moved a distance of 120 meters. So the distance from there to there is 120 meters. Determine the height of the building. How might we go about doing that? What do we know? What can we write down? Yep. Yep. Yes, you can. So we could find these angles at the top if we wanted to. Yeah, so we can find these angles here if we want to. What's the same about both of these? Anything that's the same? What we can do is we can set up one equation for this triangle involving what we want to find, which is the x and the angle, okay, and this bottom base here, because that we know something about that. And then we can set up another equation for this triangle here, involving the angle, x, which is the same, and this distance, which we know a little bit about. Okay, so let's see what we can do. Let's call this distance here L for length, the distance of the base of this thing. So it's the total distance from where he starts to the building. So what can we write down? We can write that the tangent of 19 degrees, what's the ratio that's involved here, tangent, is good. So in this case, that's opposite, which is x, over adjacent, which is L. Okay. And then we've got another equation. The tangent of 47 degrees is what? Opposite, x. But what can I write now for the adjacent side? L minus 120, yes. Two equations, two unknowns. We can solve it. Two equations, two unknowns, simultaneous equations. How would we proceed from here? So if we rearrange equation 1 for L, so we've got L equals something, we can then substitute that term into equation 2, and then we'll only have one unknown, which is x, which is what we're after. Okay? Let's have a look, because I don't want to... the idea is I'm going to give you time to have a go at these things. So, right, rearranging number 1, we've got, multiplying both sides by L, we've got L equals x over tan 19. Rearranging number 1, L equals x over tan 19. L equals x over tan 19. Putting this into equation 2, so substituting in 2, tan 47 equals x over L, which is x over tan 19, minus 120. Which doesn't look very nice, but the good news is I've only got one unknown now in here, and that's x, so in theory we can solve it using the sorts of rules of algebra that we were looking at this morning. I don't like that bracket underneath in the denominator, so what can I do to get rid of that denominator? What's the thing we always do? Multiply by it. Multiply both sides by that bracket, bring it to the top. So I've got tan 47 times x over tan 19 minus 120 equals x. Still not got x yet, but at least I've got rid of the denominator, So now, what would you suggest we do now? Expand out. The idea now is to get all the terms involving x on one side. So expand out the bracket. We've got x times tan 47 over tan 19. And at this point we could work out what that is. Minus tan 47 times 120 equals x. So I've multiplied both of the terms inside the bracket by tan 47. We could work out what they are now. That might make life a bit easier for us. What is tan 47 divided by tan 19? Making sure we're in degrees, please, when we work it out. 3.11x minus, what's tan 47 times 120? 128.68 equals x. So now we subtract x from both sides and add 128.68 to both sides. So I get 2.11x equals 128.68. And x equals 128.68 divided by 2.11, which is, so therefore x equals 60.18. Not an easy question, but I didn't, sorry? 98, thank you. So not a straightforward question, but remember this morning we're talking about the use of algebra in a surveying situation. That's exactly the sort of thing you do. You can work out the height of a building just by measuring the angle to the top using a theodolite, moving a bit closer, measuring the angle again, and then using algebra, the laws of algebra and trigonometry, to come up with the height of the building to a high degree of accuracy, assuming the building is perpendicular and the ground is flat. Okay? Big assumptions. Sorry?
I wouldn't be able to measure the height of the moving pan.
No, not that way, that's true, yeah. So the exercises you're going to do are not that difficult. You know, it's leading up to that. I've done one of the more difficult examples, but hopefully you saw roughly how that worked and you can take your time and look through. Let's have a look at another example. Page 32, problem number 7. So again, we can do this problem, and it's in the textbook if you want to look at the way they do it, but let's try it together. So we've got a force of 5 newtons inclined at an angle of 45 degrees to a second force of 8 newtons, both forces acting at a point. So you've got two forces acting at a point. Calculate the magnitude of the resultant of these two forces and the direction of the resultant with respect to the 8 Newton force. This is important, this last bit. Angles, that's telling us that all angles are going to be measured with respect to that. So the first force I'm going to draw is the 8 Newton force. And then I'm saying a force of 5 newtons is inclined at an angle of 45 degrees to that. So then I draw my second force, of 5 newtons at an angle of 45 degrees to that. So that's my reference point, is the 8 Newton force. Why is that my reference? Because everything is with respect to that. I want to know the direction and magnitude of the resultant with respect to that. So in other words, I'm after this. I'm after that resultant. It's going to be roughly like that, isn't it? I've got the two forces acting roughly the same direction, so I'm going to expect something a bit like this. And you might have done some work where you've worked out what the you've made a parallelogram up and worked out the resultant that way. Have you done anything like that before? Okay, another way to do it is what's called a top-tail method. So I do the 8 Newton force, and then I draw the 5 Newton force at the end and find the resultant that way, called a top-tail method. And that's the way I want to approach it now. Another way to do it is to find the total horizontal and vertical components of each one, and then add them together and find the resultant. And that's the way it's worked out in the textbook, because it says, oh no, it doesn't. No, I'm thinking of another example. So let's have a look at this by using the top-tail method. No, let's look at it by finding the vertical and horizontal components, okay? Because I think I've got another example later on where we might use the rules for that. So what we do is we find the vertical and horizontal components for the 8 Newton force. We find the vertical and horizontal components for the 5 Newton force, and then we add them together and find the resultant. So what we do is we draw in a right angle. So the 5 Newton force, the vertical component of the 5 Newton force will be this bit for the 5 Newton force, and the horizontal component of the 5 Newton force will be the length of this line here. The 8 Newton force is easy because that's just all acting horizontally. So for the 8 Newton force, we can say the vertical component is 0 and the horizontal component is 8 newtons. Anything I've forgotten to mention there? 8 newtons. Anything else I need to state about that? I need to state that it's acting right to the right. So convention might be plus, up is plus, and right is plus. So that means that both the vertical and horizontal components of that 5 Newton force are both positive, but we need to set the convention. So by saying that's 8 newtons, I'm saying, in theory, I'm actually saying or implying that it's a positive 8 Newton force. So what's my convention? Positive to the right. Now the 5 Newton force, what's the vertical component of the 5 Newton force? How do I find this side of that triangle? Using sine and cosine and tangent ratios. It is a sine. It's a sine, yeah. Sine is opposite over hypotenuse. If we go back to here, look. The sine rule is opposite over hypotenuse. And so the opposite is the hypotenuse times the sine of the angle. So going back to here, this equals 5 times the sine of 45 degrees. And the horizontal component is the cosine. So that's 5 times the cosine of 45 degrees. What is 5 times the sine of 45 degrees? .53. So we've got a resultant. We add up the vertical and horizontal components of 3.53 and 11.53. Adding verticals, which is 0 plus 3.53, and horizontals, which is 8 plus 3.53, gives us this. So the resultant is this line here. So we can sort of form a right-angled triangle here. So that side is 3.53. And then what do we do now to find r and theta? The magnitude r and the angle theta. Yeah, to find r we use Pythagoras. So r equals 11.53 squared. In fact, r squared is going to equal 11.53 squared plus 3.53 squared. So therefore r is the square root of 11.53 squared plus 3.53 squared, which is, so that gives us 12.06 newtons force. So we've got a resultant force of just over 12 newtons. Now all we need is theta. We've got the opposite, which is 3.53, and the adjacent, which is 11.53. You wouldn't generally use the resultant magnitude, which we just found. We use what we're given, the original values. So which ratio is to do with the opposite and the adjacent? Tangent. So we're after the angle. So theta equals the angle whose tangent is the opposite over the adjacent, which is 3.53 over 11.53. So here we're using the tangent ratio and the Pythagoras theorem to find these values. And that turns out to be angle 17.02 degrees. Okay. Just an aside worth mentioning here, actually, on your calculator, when we come to complex numbers, we'll be converting rectangular coordinates to polar coordinates. This is, in theory, a rectangular coordinate. This position here has got an x coordinate of 11.53 and a y coordinate of 3.53, that point. If I want to convert that to polar coordinates, it will tell me what the angle is in polar coordinates and the value of r, which is exactly what I'm after. And on the calculator, you might remember, if you've done this with me before, which I know one or two of you have, you go on your calculator, look at the buttons on the calculator, you'll see above the minuses button, it says polar, is it? That's telling you that if I hit that button, I can convert to polar coordinates. So hit shift polar. Is it shift plus then? That'll give you polar. And then enter the coordinates. X first, 11.53. And then a comma, which is above the closed bracket symbol. So you hit shift, close bracket, and then the y coordinate, 3.53. And then equals, and you get r, which is hopefully roughly 12.06, and if you scroll along you'll get theta, which is 17.02. So that's a bit of a shortcut, okay, to finding. We can use that button to resolve, to find the resultant of a vertical and horizontal force, because it allows you to convert it to polar coordinates, which is exactly really what we're doing here. Handy, okay? Yeah, that's going from polar to back to xy coordinates again, is the other button. The next example I want to look at is on page 227, this work problem 9. Let's have a look at it. So again, I've tried to pick one that you might come across. So we've got two forces, or two vectors again rather. This time the vectors are voltage phasors, so they represent voltages. And voltages can be in and out of phase. So we can talk about, again, a voltage V1, which is our reference voltage, and then a voltage V2, which is at an angle of 45 degrees to that. And so what we want to know is what is the resultant of those two voltages. The resultant of 40 volts plus 100 volts is not 140 volts if there's a phase difference. We have to set them out like this, and again, find this resultant here. What's the value of that resultant? Well, we could use a similar method to the one we've just done. We could find the vertical and horizontal components of each, and then add them together and find the, use Pythagoras and then the tangent ratio. Or we can use the cosine rule for a for a triangle rather, which has got no right angle in it. This triangle's got no right angle in it. And I know from this triangle that the length of this side is 100 volts because V2 is 100 volts. I know the length of this side is 40 because V1 is 40 volts. And I know this angle is 45, so therefore I know this angle here, which is 180 minus 45, 135. And then I can use the cosine rule. I've got two rules that I use, and this might ring a bell with some of you when we look back at the notes that we're looking at. There's two rules that we use. One is the sine rule. Here it is. And the sine rule can only be used if we know a ratio. We know a side and the angle opposite it, you might remember. You've used the sine rule before. So we can only use the sine rule if we know any side and an angle opposite it. In this particular case, we don't, so we have to use the cosine rule, which I've just noticed I didn't finish off. It's a squared equals b squared plus c squared minus 2bc cos a. So if we can add that. Very important omission. I don't know what happened there. And that's what we're going to use here. So in this example, we know if we relate this sine and cosine rule, the sine and cosine rule assumes we've labelled the angles A, B, C. So therefore that's side A, side B and side C. So that's the convention for labelling these sides in the triangle. So again, I repeat by saying that the sine rule can only be used if we know a side and the angle opposite it. A and angle A, or C and angle C, or B and angle B. In this case we don't know that. We know angle B, but we don't know the side opposite it. We know side, this side here, call that side A, but we don't know angle A, and so on. So we can't use a sine rule. So what we do is we say a squared equals b squared plus c squared minus 2bc cos A. That's the cosine rule. And how we use it is very straightforward, actually. The side we're after, in this case that's this side, r squared equals, it turns out to be just the other two sides, it doesn't matter which one we call which, the other two sides squared and added together, minus 2 times the other two sides, times the cosine of the angle opposite r, which is what we're after. So we just plug in the numbers. It's 40 squared plus 100 squared minus 2 times 40 times 100 times the cosine of 135 degrees. Done. Plug that into the calculator and out comes the answer, but of course that's r squared. So r squared is that, so r is the square root of that, which is okay, and that's volts, because we're talking about voltages. So in fact, the resultant voltage of those two voltages is 131.4 volts, not 140, the addition of the two. Okay, let's go back to the start. So what I've attempted to do here is just give you an example of each of these situations where we might use the sine, cosine, tangent ratios, where we might use resolving forces, use those in resolving forces together with Pythagoras, and where we might use the sine rule or the cosine rule, these two rules here. Now, I'm anticipating that some of you will know, remember doing some of this sort of stuff before. So what I'm going to say now is, here are the exercises, have a go at some of the questions, okay? And I'll help you if you get stuck.